today what I mainly wanted to do was to kind of go over again about the harmonic oscillator, and because I think in some sense there's it's kind of often said that in physics that the harmonic oscillator is kind of the most fundamental thing that a lot of physics courses are kind of just teaching you more and more sophisticated things you can do with a harmonic oscillator, and that's certainly true of a lot of this class from this point on. So I'll start, but so we've been sticking to a harmonic oscillator with 1 degree of freedom, and a lot of what I'll do next semester will be to show you what happens if you have more degrees of freedom, or if you have an infinite number of degrees of freedom. But for today in this course, we'll stick to 1 degree of freedom. And then there's something. Then the other thing I want to try to get to today, say a little bit about, is about another kind of important topic that comes up when you start thinking about the harmonic oscillator. You find that there are these other interesting sorts of states, which are not the energy eigenstates, but which are called coherent states. And I want to explain those, and I also want to explain how they fit into the story I've been telling you about the Heisenberg group and its representations. Okay, so let me get started. Let's get back to the harmonic oscillator. Start again with the harmonic oscillator. So just to kind of to summarize again, the kind of standard point of view is harmonic oscillator. Sure. Oh, and also what I'm doing here, I'm going to I was keeping track of a lot of the various kind of constants that normally appear in this problem, but from now on, what I'll do is I'll mostly set h bar equal to 1, and also the mass equal to 1. And sometimes there's one remaining constant in the problem, which is on this omega. That's kind of crucially going to be kind of the frequency of the kind of fundamental frequency of this problem. And I'll often also set that equal to 1. So there may be at some points I might want to actually introduce that so you can see how that appears. Okay, but the really what this is this so the classically this is just the theory of 1 degree of freedom. So the phase space is just 2-dimensional. It's got given by coordinates p and q, and the Hamiltonian function is just a half q squared plus p squared. So from the Hamiltonian point of view, one nice thing about this thing, one of the great things about the harmonic oscillator, is that it's kind of completely symmetric in q and p. So and this is actually one of the great arguments for the Hamiltonian point of view as opposed to the Lagrangian point of view. From the Hamiltonian point of view, you have this beautiful symmetry, and a lot of what's happening in the harmonic oscillator is governed by the fact that this h kind of this function h just generates it generates rotations in the plane, and so there's kind of a anyway kind of the fundamental geometry of phase space and Hamiltonian mechanics works out very, very nicely here and gives you stuff which is harder to get from the Lagrangian point of view. But anyway, so now if you quantize, so the standard way of quantizing in position space is just to take the Hamiltonian operator to be a half p squared plus q squared. And if you do this in the position representation, this is then a half and then minus the derivative plus q squared. Okay. And so you look for let's say so you take h. So the problem is to find eigenfunctions of the Hamiltonian in the state space, which now nothing is going off to all the state where there's a nice there's going to be a nice basis of localized states. So this is going to be just L2R, and normally you work and so this is in the position representation. Actually, maybe the thing to notice here is that you could, because of the symmetry between position and momentum, if you Fourier transform and work in the momentum representation, you get essentially the same equation. It's just that this guy becomes a ddp squared, and this guy becomes just multiplication by p squared. So it's the same problem. And this is a case in the free particle problem. Going to momentum space kind of diagonalized the problem and made it easier to solve. Here, if you go back and forth between momentum and if you Fourier transform between momentum space and position space, I mean nothing. You just get back to the same problem. Okay. Then so, but now then the answer is that the energy eigenvalues. So eigenvalues are numbers En, which is n plus a half, and if you want, you can put in h bar omega here. So these are the so-called quanta of energy, and in some sense maybe it's kind of this problem again is kind of the really kind of fundamental reason why it's called quantum theory. That what this is saying is that the states are kind of labeled or have this quantized nature, and they can be thought of as up to this weird a half. They can be thought of as just some kind of collection of so-called quanta, each with energy h bar omega. Okay, and then if you write out the solutions to this thing, you get one way of getting it is these are psi. The eigenfunctions are just given by, even with the right normalization, 1 over square root of n factorial, 1 over square root 2 to the n. And then you just apply this differential operator q minus d dq n times, taking the half q squared. Okay. So this is maybe the simplest way of writing down these eigenfunctions. And so this is just going to be, so this is going to just give you some polynomial q, okay. And what you end up with, and so as n gets large, you end up with some kind of complicated polynomial in q. And the interesting thing about these, these are called Hermite polynomials. Right, all right. And then these and the interesting thing about these guys is that for different n, these guys are going to be orthonormal with respect to the standard inner product on L2 of R. So they give you kind of these polynomials times Gaussians give you kind of a nice orthonormal basis on L2 on the L2 functions, and that has all sorts of applications, in all sorts of areas of math and physics. Okay, now, okay, so this is in the position basis, and as I said, if you Fourier transform, you're going to get the same, basically essentially the same formula as with q replaced by p. You're not going to get anything different. But there's another, the other basis. So this is kind of a complicated basis to work in, and in some sense, if you choose to just work in terms of momenta or position, you've kind of broken the symmetry between position and momentum. There's this nice symmetry of rotation in the momentum position plane, which you've kind of broken by a choice of position or momentum, and that's making your story more complicated. So if you want a story that kind of preserves that symmetry better, or that in some sense, the point is we're looking more for a formalism where there's a U1 symmetry of the thing, and we want to diagonalize that U1 symmetry. We want to diagonalize the things with constant weights, And so that's going to be another. So you could instead you could think of H as having a basis, and I'll call this N, where so you can just kind of abstractly think of this as being is basic number N is equal to 0, 1, 2, etc. with N1, N2, with delta N1, N2. And this is sometimes called the occupation number. And so when you're doing calculations in this subject, you often can instead of trying to work in terms of wave functions, you might as well just work in terms of in terms of complex linear combinations of these basis states, just labeled by a non-negative integer. Okay, and then you can recover wave functions by what you do is take, well, there's the standard formalism for going back and forth for changing bases in this Hilbert space by and so you would have in the Q that the one of these guys in this Q basis is given by these side. So if you want those wave functions, you can think of as being the kind of the things that tell you how to go from the basis of written in terms of these of the ends to the basis written in terms of delta functions of Q. It's kind of the transformation of bases between these two bases are given by those functions. Okay. And maybe just to say just a few words about what happens in higher dimensions. So from this point of view so far, that what we said so far, I mean, nothing much really interesting happens in higher dimensions. What you just have is that the eigenvalues, if you have d degrees of freedom, in other words, you've got dq's and dp's. Then what you can do is you have the wave functions. The eigenfunctions are, well, then h is just the sum from j is equal to 1 to d of 1/2 pj squared plus qj squared. It just breaks up into a sum. So everything where so these things behave independently. I mean, physically you can think of these as being these quantized oscillators, and they just don't know. There's no interaction. The different ones don't really. They all behave independently. It just behaves like a collection of d different ones of these things. And so what you have is that then you have the eigenvalues are given by E, and then so you just have to pick a list of n non-negative integers, n1 up to nd. It's just n1 plus n2 plus nd, and then you've got d halves that show up. So it's that, and then the eigenfunctions. They're psi. They're again labeled by these integers and d, and they depend on d variables. And what do you want to do? And so these are just these are just given by the product of the one-dimensional things. Q1 Q2, and this is just going to be some polynomial in Q1 QD, and then a Gaussian. QD, sorry. Anyway, so there's really nothing from this point of view of Q space and everything. Nothing really interesting happens. What the more interesting things to talk about, which I'll talk about more next semester, are that once you have more degrees of freedom, you have a larger symmetry group. Here, in some sense, in the 1 degree of freedom thing here, in some sense, you just have this symmetry, this U1 symmetry generated by H. In higher dimensions, in D dimensions, you're actually going to have a U of D symmetry, which is going to be interesting to talk about. But you don't, and that's kind of hard to see from the. That's a symmetry which mixes P's and Q's, which is hard to see from this point of view. But that's pretty much the. Okay, so that's a standard thing. Also standard then is to kind of start moving to the this other kind of formalism we want to use, which is a formalism which has this U1 symmetry built into it in a much more interesting way, which is that you define okay, so you define A is 1/2 1 over the square root of 2 Q plus IP and a dagger minus IP. Okay. And then the idea is you work with these things instead of the Q's and P's. And the point is that these things are the things that really have a nice property that under this kind of under a rotation in the QP plane, these things behave separately. This thing behaves like either the I theta. This thing behaves like either the minus I theta. So this kind of separates out this kind of diagonalizes the SO2 or U1 action in the QP plane. But it does so in a very tricky way that it kind of complexifies everything. But you've introduced. You're now looking at not self-adjoint operators, but complex linear combinations of self-adjoint operators that aren't necessarily self-adjoint. But what you do is you instead of the Heisenberg commutation relations, you just work with this guy 1, and the Hamiltonian is 1/2. Hamiltonian is one way of writing it is A dagger A plus 1/2. And this operator is a number operator called n. And last time I showed that this thing has and that operator acting on these nth, this occupation number n energy eigenstate is diagonalized and get it with eigenvalue n. Okay, and then the other. Then these things are so-called raising and lowering operators. What if you take n and apply it to this, you get, let's see, what's the right coefficient? You get the square root of n times n minus 1. And if that's a lowering operator, it reduces it by 1. And notice that what happens is at and it also crucially satisfies this. It annihilates the lowest energy state. So, and then this guy raises, this guy does the square root of it, and So what these operators do is there's a lowest energy state, and these guys move you up and down it. There's some lowest energy one where if you try to move down, you can't. You're gonna hit zero. And just from the property of, I should say that if all you know is the property is this property, then you have to watch out that in principle you could have you can actually have eigenvalues going, up to an anyway the possible systems you can get that are going to satisfy these with these operators. The states are going to have to be separated by one. And for a number operator, there's been a number operator that separates them by one. But in principle, that number operator could go up to positive infinity or down to negative infinity. So built into this formalism in a not necessarily obvious way, often by choice of what the number operator is. Is it this or a dagger? That you made a choice whether your system is going to be states that have positive energy or states that have negative energy. So there's kind of a symmetry between positive and negative energy here, which you've broken by some choice. Okay. Then.
Sorry.
Yeah.
So just to make sure I understand your point. So if we choose a Hamiltonian to be instead of a dagger a but a dagger, are you saying that then we just get or something like that kind of variation, then we just get negative energy?
Yeah. Then instead of being at zero and going up, you'll be at zero and then go down to negative infinity. I mean, all I'm really saying is that you really can you can interchange the role of the this form you can interchange the role of the annihilation and creation operators by you could swap them back and forth and at the cost of, instead of having states that go up to positive infinity, they go down to negative infinity. So then this state would be characterized, instead of being characterized by this, it's characterized by the state that can't be raised. Okay. Anyway, so this is just, I don't know. This kind of appears, this issue appears in some funny ways at some points, but it just anyway, yeah. It's something I realized when I was actually, if you look at the anyway, it's typical of quantum mechanics that there's various points at which you have to make a positive energy assumption. And if you don't make that energy assumption, then then you can get some different phenomena. So here we're assuming this can't happen, and so it has to be either go all the way down or it has to go all the way up. So it's got to go all the way up. Okay, so now let me okay. So now what I want to do is I want to get back to this point. I want to kind of go back to the beginning, go back to the idea that quantum mechanics is really this that we're looking at the kind of up to unitary equivalence, the single interesting representation of a Heisenberg Lie algebra. And the Heisenberg Lie algebra is something you get by looking at phase space with its Poisson bracket. But the idea is to try to get to this point. We can go back and start with phase space, but we can actually introduce some complex numbers on already in a classical theory. So the idea is to kind of go back and complexify phase space. And then what you do is you define Z. So take coordinates, and then you can use. So in some sense, our problem with phase space was that we had these Q's and P's with these nice Poisson brackets relations, but there was this interesting, if we rotated our phase space, we moved Q's into P's, and we couldn't, we really would like to diagonalize that rotation symmetry. And so to do that, you use coordinates Z, right, how do I do this? Is 1 over square root of 2 Q minus IP So we use coordinates that are on which are complexified, which are coordinates on our phase space, our normal phase space, but complexified. So that we've allowed not just real linear combinations of elements in here, or real linear combinations of Q's and P's, but we're also allowing complex linear combinations of Q's and P's. And in some sense, the basic idea is that if you do this, then this becomes, this can then be broken up as C plus C, where this guy is, the Z's are the coordinates here, and the Z bars are the coordinates here. And this is something you saw way back at the beginning of class when you asked it to look at what representation you get by SO2 acting on by rotations on the plane. Well, if you want to think in terms of complex representations, you have to complexify, and then you get 2 complex representations, a weight 1 and a weight minus 1. Let's see. And now so now what we could do is instead of H is equal to functions of Q or functions of P. So the crucial thing about quantum mechanics, a way in which it's really different than classical mechanics, is that you don't, your observables, or you don't work, states don't depend upon on arbitrary functions of P and Q. And to understand what a state is, the space of states, you have to pick kind of half the variables in here. You can't have states cannot be arbitrary functions of Q and P. If they were, you could kind of localize a particle, give it a fixed Q and a fixed P, get it closer and closer. And you can't do that. It has to be either functions of Q or functions of P so far. But if you do this, you have another choice, or, and this is what we're going to talk about now, functions of Z. Or you also could also work the other way, or Z bar if you like. But we're going to pick one of these, and we'll pick. I think I went back and forth the choice several times in writing the book, but I think I made it Z. Okay, and so now. So what does it mean to be? Well, the tricky thing here is to notice is that an arbitrary function, C function on R2 is a function. Let's call it f of z and z bar, right? I mean, so saying that you have a function that depends both on p and q, you could just use this, and you're throwing in complex numbers. That's kind of equivalent, you can just change variables and say that I've got a function that it depends on z and z bar. If I want to write it, I have to tell you what to do. Put some kind of functional dependence on a z and on a z bar. Now Okay, so now there's a story which you to really understand the details of, you have to have studied complex analysis. And so but in complex analysis, there's the idea that it's really interesting to focus not on any function of z and z bar, which would be equivalent to looking at any function of p and q. But if you want some analog of just looking at half the functions in some sense, you want to look at the ones that just depend upon z and just depend upon z bar. So for instance, if you want to stick to polynomial functions, you want to look at functions that you can write down by just taking polynomials in z and not using z bar. And so these are going to be so we want functions that only depend on z. So you have to be a bit careful about that statement, because what does it mean? Z bar is just the common conjugate of z, so they're clearly related. So if it depends upon one, you think it depends on the other. But here, meaning that if you take the derivative with respect to z bar of your function, you get 0. Okay, so this is what we mean by not mean you can, this d d z bar is just d over dx plus iy, and so you can write down this equation. This is going to be a pair of equations. They're called the Cauchy-Riemann equations, and the anything which satisfies these equations we think of as only depending on z, not z bar, and the name for it in mathematics is holomorphic. Okay. So what I'm arguing is that there's another possible way of studying the harmonic oscillator or studying any of these quantum mechanical systems is going to be to take your state space not to be functions of q or functions of p, but holomorphic functions of z. And this lands you in kind of a different area of mathematics where you're looking at complex function theory, but and that makes some things trickier. It also, these things have all sorts of magical properties also, which give you interesting things in the formalism. Okay, so that's that. Okay.
So I'm still a bit confused about why we want functions that only depend on z, not z bar.
Well, I'm saying, well, okay. Well, I mean, if saying that if you're looking at complex valued functions, saying that they depend upon z and z bar, any function of if you have any function of q and p, right? You can just rewrite q is z plus z bar, right, and p is z minus z bar. So any function of q and p gives you a function of z and z bar, right? And similarly, if you have z and z bar, you can write them this way, and you get complex value functions of q and p. So clearly, if I say that any kind of function you write down of z and z bar it is allowed, that's going to correspond to saying that any function of q and p is allowed, and that's going to be too big a space. That space is not. That cannot be a quantum state space. It's too big because it's going to include things like localized functions where q and p are both localized near a certain value. So you're going to simultaneously know what q is and what the momentum and the position of a particle are. Okay, so you have to somehow get rid of the function space of these guys is too big, just like and it's the same in space with these guys. It's too big. You have to somehow get rid of half the degrees of freedom. Just like you had to say that your functions didn't depend upon P or they didn't depend upon Q. Well, and what I'm just saying is one thing you can try and do, which turns out to work, is to make this statement that I have to kind of get rid of the things that depend on z bar. And if you stick to polynomial functions, then it's kind of trivial. Just you only allow yourself to write polynomial expressions in z. You don't allow any z bars. So, but it's it does to make more precise what you're saying. Does not, because when I say only depend on this, not this, there's something funny going on because these two are related. So this is actually the precise statement. Okay, does that help?
Yeah, that's helpful. Thanks.
Okay, so that's okay, and then we'll get back to this later. Something I said at the end of the last time, which is so we're gonna just say that our state space are as holomorphic functions on this complexified phase space, but they're not the thing which I'm not telling you here, which you have to watch out for, is what the inner product is. So we'll get back to that question again, but you already kind of saw that at the end of last time. So to really specify what H is, I have to not just say that, but I also have to say what the inner product is going to be. Okay, but before I get back to that, let's go back to then just as a matter of kind of philosophy, the idea was that.
Is there a question?
Yeah.
So does this mean that if we write every energy eigenfunction which only depends on Q, that in terms of Z and Z bar, then this function is holomorphic?
No. Yeah. So you can't. Yeah. So the interesting thing about this, you'll see, is the relationship between. There's a very interesting relationship between these holomorphic functions, between functions of Z and functions of Q, and it's called the Bargmann transform. And I may get to it at the end of today, or I might talk about it next time. But you can't. Yeah, the thing which is not true is you can't just take a function of Q and plug in, Q is equal to Z minus Z plus Z bar, and then because if you did that, you would have a function of Z and Z bar. So the relationship between these holomorphic functions of Z and these functions of Q or these functions of P is much more subtle than just using these things. Okay.
So does this mean that the energy eigenstates are not legitimate states in the transform space?
Okay. So yes. So the energy,
they are not holomorphic functions.
No, the energy. So maybe the energy. Let me see. Was this the next thing I was going to say here? Well, maybe in a minute. Let me just say. So the energy eigenstates. Let's say that. So the energy eigenstates of your harmonic oscillator are Z to the n. Okay, but so Z. So you have to have the transformation between between holomorphic Z space and between Q space. Remember, so these are these Q minus ddq, whatever it was, to the n e to the minus q squared, right? Yeah. So this is what's called the Bargmann transform. But it's quite tricky, you see, because yeah. So the really nice thing is that the energy eigenstates are kind of the simplest possible holomorphic functions of Z. They're just the monomials. Okay, but this is definitely not what you would get by if you plug in Q is equal to 1. What is it? Yeah. Anyway, put Q. So whatever, it's the square root of q to z. Anyway, if you plug in q is equal to z plus z bar, you're not gonna get this. You're gonna get some horrible thing which is not that. So so that's not what's going on. But I mean, this is a legitimately very tricky thing. The fact that this transformation you're doing, going from this functions of Q, functions in the real not, so this is kind of L2 functions on R, and this is holomorphic functions on C with a certain boundedness condition. And it's actually a quite beautiful and very subtle piece of mathematics about how you go back and forth between these. Okay.
So this means that when we go between different state spaces, we always need some special transformations rather than just write out coordinates transformations.
Yeah.
Just like we need Fourier transform to go between the position space and
yeah, I mean, it's something a little bit like the Fourier transform. I mean, the Fourier transform is a nice symmetric thing. It takes L2 to L2. This takes L2 R to some very different kinds of functions. But it is a one-to-one unitary transformation. I mean, this guy you made into a Hilbert space, and then this is a unitary invertible transformation between the two things. But it's a very tricky. It's a tricky one. And again, the formulas in the notes, I may get to it next time. But the formula is very, very non-obvious and not so the bottom line is that if you stick to working in occupation over space, or you stick to working in with these holomorphic functions, everything is very, very nice. You get very, very simple calculations. If you stick to here, you get a somewhat more complicated story, but it's still tolerable. But trying to move back and forth between these is actually very hard. It's really not. It's not a simple relation. Okay. So let me then go back to what I wanted to say. Is so then the idea is to go back to the beginning and say what we're doing. So remember what we did was we said that the Lie algebra of the Heisenberg group in 3 variables. So what was given by, it was this, but you took R2, which was your phase space with a basis of P and Q, and then you added in a one-dimensional space with a basis of 1, and then you put in the Lie bracket Q P was the Poisson bracket is equal to 1. This was the real story about the Lie algebra of the Heisenberg group. Now, if you want to go, now what we've done is here, if we try and use these z's, or we try and take complex linear combinations of these, what we've done is we're looking at Lie H3, and then we're complexifying, and that's the same thing as, so that's going to then be a C plus a C. Here you're going to have the z's, a z bars, and then you're still going to have 1 here, but you're going to allow complex coefficients. So, but the usual thing about Lie algebras is that even though Lie algebras are kind of real vector spaces, that if you you can complexify them kind of for free, and they have the same bracket structure. You still have the same bracket structure and everything. There's not any real, well, and anyway, you can complexify any Lie algebra and get essentially something that's very, anyway, essentially the same thing over the complex numbers. So that this is what we've done here, and we took the here we had, what did I have? Was it a and I think it comes out that you get so here you get the non-zero bracket relation is just that z bar, I think this is the right one, is equal to I. So what we're doing when we go into this world is we've taken this nice real algebra and we complexified it. But now the nice thing is that this R2 has split up this way, and we can and when we can quantize by looking at just functions that just depend upon our state space will just be just functions of z, just like we took just functions of q. But then quantization. So what is quantization? It's basically the same story as in the Q and P. It's still a canonical quantization, except complexified. And what it really says is that you have a representation gamma of H3. Well, let me say gamma prime of this gamma prime of this complexified algebra on H is equal to holomorphic functions of z, and then the way it works is that it takes this one here to just, I mean, you want to retrieve the same representation that the Schrodinger representation that you had before, which was unitary on the real things here. So on the one, it should just be minus I times identity, just the same as in the real case. And then on Z, you take it to be minus I times, let me get that right, A dagger. And on Z bar, it's minus IA. Okay, and so the same story that I was telling you about how to think of canonical quantization as being just the construction of just the one kind of standard interesting representation, infinite-dimensional representation of the Heisenberg algebra. Well, this is the same thing except the complexified Heisenberg algebra. And instead of everything being in terms of operators big P and big Q, here it's going to be these guys. And then these guys, we then, what they do is you take then A is equal to ddz, and A dagger is equal to Z, okay? To get the right commutation relation. Okay, so this is kind of a complexified version of the standard story where we've already been given, but it's not. And but the interesting thing about it is that it has states expressed in a very different way in what you're used to, and it has built into it this kind of splitting into weight +1 and -1 under rotations in the PQ plane. Okay. Okay. So that's this. So now what I wanted to do, I mean, there's these things called coherent states that I wanted to talk about, and there's a standard kind of discussion of these things in the you'll see in the physics literature. You'll see them, and they're quite beautiful objects. But I wanted to kind of re-express the kind of standard discussion of these things in terms of this representation theory was kind of, it struck me as kind of nice application of thinking about the Heisenberg group and the Heisenberg algebra. Actually gives you a nice understanding of where these coherent states come from. So let me kind of state that first abstractly. Just get rid of it. So this is the really new idea for today is this, our coherent states. Okay, and the so the thing to notice about coherent states is that the harmonic oscillator problem tells you something has something interesting about it, which is not so much true in the theory of a free particle. But there's a distinguished you use the fact that zero is a distinguished state in H. So from the point of view of thinking about your standard quantum mechanical state spaces, as if you thought of it as being the state space of a harmonic oscillator, or if you thought about it in terms of this harmonic oscillator Hamiltonian, then one interesting thing you've done is you've picked out a distinguished state, and actually in the position representation, that distinguished state is the Gaussian state. It's the Gaussian state such that if you do a Fourier transform, you get back the same thing. So and also from the position space representation has a very well distinct. So this is one. So it's equal to just one as a holomorph for H holomorphic functions, and it's equal to e to the minus 1 over half q squared for H is L2 of. So in either one of these representations, there's this kind of unusual distinguished state, and when you go to quantum field theory or higher dimensional harmonic oscillators, the fact that the existence of this distinguished state, which kind of is the thing with no quanta in it, as opposed to other states which have quanta in them, that it plays a very unusual role. But from the point of view of holomorphic functions, it's just one. And again, you can see that the Bargmann transform has to take one to the Gaussian, so it's something funny is going on. Okay. And then now what do you do if you're given a distinguished state and you have so canonical equation says that the H is a representation of the Heisenberg group H3. You can act with H3 on 0. So you can take the state and then start act, and if you act with a Heisenberg group, it's going to move it around, and you get a family of finite dimensional. Well, let me say it this way: family of states in the infinite, H. Okay. So the coherent states, in some sense, morally, what they're going to be is they're going to be states of this kind. So they're states that have special properties, and the reason they have special properties is that they're closely related to this vacuum state, and that they're basically just things you would get if you applied some element of the Heisenberg group. So if you exponentiate this Heisenberg, the algebra representation you have, and then you act with a Heisenberg group on this particular state, and then you're going to get a family of states, and these essentially are the coherent states, at least morally. So I'm going to give you a lot of formulas, but before I get to a lot of the formulas and the formalism for precisely talking about coherent states, I just wanted to kind of give this moral justification for what they are and why they're interesting, because it's a nice justification, I think, of the point of view of representation theory about all of this. And there's also actually you also find something similar happens actually in the if you're interested in representations of of the spin group, you something actually similar happens. In the case of a spin group, there's a distinguished state, which is the highest weight state, and then you can act. And if you act with the highest weight state on the highest weight state by the spin group, again you get a finite dimensional family of very special kinds of states. These are the things that you get by acting on the special state, the highest weight state, and those are called spin coherent states. So there's a nice story kind of wherever you go, whenever you've got a version of representation theory where there's kind of a distinguished kind of something that's like a lowest weight or highest weight state or something. There's a special state where you can't go any higher, you can't go any lower, and what you get by moving that around are these coherent states. Okay, but now let me give you a formalism for what these things actually look like. Yeah, so here, this gets a little bit this gets a little bit technical, and there's some technical calculations about this and keeping track of coordinates. And I did try and work this out carefully in the book, so I won't go. I'm going to go a little bit fast in some of that, and not go through all the details of that, and try to emphasize, just get to the point where you actually have to show you how to get some formulas that are actually useful. But the idea, here's the idea, is that G, you can label elements of G of H3 by let's see what I want to talk about I want to do this alpha. I want to see and sorry, gamma. Actually, maybe sorry. This is not I'm trying to say this. Yeah. Well. Okay. Anyway. Let me. Yeah. So in some sense, what's again? I won't go through the details of this, but this is a three-dimensional space, and if you want to put kind of local coordinates on it, you can locally choose a complex number for two of the coordinates that are in the phase space. In your phase space, and you can choose a gamma for the kind of central direction, for the central that moves in the central direction. But they're to really say this right, I really should think of these as coordinates on the Lie algebra, and then these are these are kind of exponential coordinates on the group coming from these kind of fairly standard coordinates in the Lie algebra, and that's worked out in the in this chapter. But anyway, you have to. If you just believe me that I can label elements of the group this way, then what you find is that gamma is this gamma of alpha and gamma. So this representation at this point in the group is you can actually construct it. You can actually exponentiate the Lie algebra representation and get this. It's e to the alpha a dagger minus alpha bar a minus I times gamma. And this part of it I'll often call d of alpha. So you can exponentiate the action of these raising and lowering operators and get and actually get the true group representation of this guy in terms of these unitary operators. Okay, and so what we want is we want to understand what happens if you apply this to zero. So if you apply in a much more practical sense than this abstract nonsense, what I'm asking about is, I'm saying, okay, if you write down this unitary operator and then apply it to the vacuum, to this distinguished vacuum state, what states are you going to get? Okay. And now to make this kind of annoying, so there's kind of an annoying phase which kind of causes trouble as you try and work through this, and because so something really interesting is happening and something really boring is happening here, which is just changing the phase. So what you do when you're thinking about coherent states is you generally think of them. You tend to mod out the phase information. You basically look at states and identify the ones that are just related by e to the I gamma. Okay, or so anyway. So we're not gonna. So I'm gonna be interested really in what this operator does, and these guys, these e to the I gammas. I already know what that does, and it's not very interesting, and I'm gonna mostly just make it go away and not keep track of it. So what I want to do then, so here's the concrete definition. The real definition of a coherent state. And this is what you'll see you'll see in a more conventional discussion. So this is the definition of a coherent state. It's given by, what you want to do is you want to say that it's alpha, it's labeled by some element, by some complex number, and what it is you take the ground state and then you multiply it by e to the alpha a dagger minus alpha bar A. Okay. So it's basically the thing which gives you the Heisenberg group action with the phase information thrown away. Okay. And now what we want to do is then if you start doing calculations of this thing, you always want to use this kind of simple version of the Baker-Campbell-Hausdorff formula, which is this. We want to use the BCH formula, which says that e to the A plus B is equal to e to the A, e to the B, e to the minus a half A, B. Okay, and then this occurs if there are no higher commutators. If the only non-zero commutator between is that anyway, if you took more commutators between A and B, higher commutators, they'd all be zero, and that's how that's going to be true for things like this. So we're going to use this relation continually to calculate this thing, and then for instance here, what you get is that this is equal to e to the alpha a dagger, e to the alpha minus. What did I do? That's alpha bar A, and then e to the minus alpha squared q, if you compute that thing, and then 0. And then what you do is you find that most terms that the A annihilate 0. So this thing is all the terms in this are going to annihilate it except the 1. So this is, and then this is a constant. So this is e to the minus alpha squared over 2 e to the alpha a dagger 0. Okay. And you can write this as, and sometimes you'll also see that this is just the definition of a coherent state. But anyway, if you write this thing out, it's e to the minus alpha squared over 2, and then then there's a sum infinity, and you get an alpha to the n over n factorial. And then now here you've got an a dagger to the n, and you use the fact that a dagger acting on n gives you the square root of n n plus 1, or square root of n plus 1, square root of n plus 1 n plus 1. So you're going to get this guy, n. And so I'll also, okay. So you can rewrite these coherent states, these alpha, can be what they are can be thought of if you try and think of them in the occupation number representation. In the occupation number representation, they contain an infinite number of things of different occupation number. Okay, so these are going to, what these are going to be is they're going to be states that don't correspond to a fixed number of quanta, but they have kind of arbitrary large numbers of quanta in them, but with coefficients that are getting smaller. They're getting smaller and smaller as you go up. Okay, that's this guy. And then now what you're going to do, and here I may start. Let me start. Okay, so you calculate a alpha, and let me not and the calculation is just going to be okay. Let me anyway. So if you calculate a applied to this guy, you quickly should find that this is actually, you're actually going to get alpha times, you're going to get back the same state multiplied by alpha. Okay. So another way of thinking about coherent, maybe even a simpler way of thinking about what coherent states are, is coherent states are eigenstates are eigenstates. It's for the annihilation operator A. Okay, but there's something now you have to watch out though. Normally, when you're doing quantum mechanics, typically you're given some operator, some observable operator, and it's a really good idea to try to find an orthonormal basis to try to look at all the eigenstates for that all the eigenfunctions for that operator, and use that as an orthonormal basis for your state space. But you have to watch out that so here the thing to say is watch out. Watch out. So A is not self-adjoint. And one way it's obvious A is not self-adjoint is that the alphas are not real numbers, but they're actually complex numbers. And so the alpha are not an orthonormal basis. And there's another calculation which I do in the book, which you can do, which gives you this. You find that if you want to find beta, if you take two coherent states, one with eigenvalue alpha and one with eigenvalue beta, and you look at their inner product, well, if you take the square, you can compute this from this expression that I erased. You can compute it without too much trouble, and what you get is that this is e to the minus alpha minus beta squared. So as expected, these things are normalized. They're normalized, but they're not orthonormal. Okay. So what you've created this kind of you created this kind of two-dimensional family of states labeled by a complex number, which at for alpha is equal to 0, it's the ground state of the harmonic oscillator. But as you move away from it, you get new states, but you get different states. But these states are are eigenvectors for A with this complex eigenvalue. Okay. Then so maybe then just to end up with a couple of kind of things related to the physics of this. So notice. So what you so there's something kind of funny here. So what you're saying here is that well, what you'd like to say is you'd like to say, you know, A is 1 over the square root of 2, what is it, Q plus IP. And so you'd like to say, would like to say that the real part of alpha is the position, and the imaginary part of alpha is the momentum. In other words, so you'd like to say that alpha is Q plus IP. Yeah. Anyway, but this doesn't really work, because you know these are not, because this is not a self-adjoint operator, and Q and P are not commuting operators. So you can't, if you first look at this, when people first looked at this, they said, aha, great, we recovered quantum mechanics. We found the states that have a well-defined position. They have a well-defined value of alpha, so they have a well-defined value of position and a well-defined value of momentum. Great. But the problem is that they don't actually, they aren't actually Q or P eigenvectors. So they don't actually, these things don't live at a specific value of Q or at a specific value of P. But they kind of, these, another reason for saying what's interesting about these things is that they're kind of about as close as you're going to get to some kind of classical behavior. So what you find is that if you so maybe let me just say one more thing where the again the calculation is in the book, so that if you have a coherent state alpha 0 at t is equal to 0, then at later times, so it's going to evolve to e to the minus I ht alpha 0. Okay. But remember, but you can compute what this is. So if you rewrite this as an infinite sum of things with fixed occupation number, and you use the fact that h is just a half plus n on the state of occupation number n, then what you can derive is and again I'm skipping a couple steps but that are in the book, you end up that this is e to the minus I a half, and I'll put the h bar omega back in, e times e to the bar omega t alpha 0. So the way a coherent state evolves in time is if you start out with something that's a coherent state at a fixed time, then the way it's going to evolve under this Hamiltonian, harmonic oscillator Hamiltonian, is it's going to pick up a phase, and this is kind of a, anyway, this is just kind of, it just picks up a phase proportional to the time, which is not interesting. This corresponds to that weird half of the ground state energy, but normally, so that's not so interesting. But what is interesting here is that the label of the coherent state just evolves just by rotation in the plane. So this is just the usual. So this is the usual classical rotation in phase space. So what's happening? I mean, if you ask about the harmonic oscillator and think about it classically, what it really does is just that if you're at some point in phase space at a given time, in later times you just move around in circles. Okay. Well, it's the same thing here. If you start at a particular point, alpha 0, think of it as a label of a point in phase space. It's just going to move around in circles in phase space. This way, and so it's going to be so the way Q and P are behaving as a function of time is exactly the classical evolution. So not only do these states seem to have a well-defined position momentum, but this position of momentum evolve in time under the harmonic oscillator exactly as they're supposed to classically. So it has these nice kind of classical kinds of behavior. And anyway, so maybe that's all I really want to say about these states right now. And in terms of the physics of these things comes about if you want to think what they are physically. They're states again which don't have they don't have a well-defined number of quanta in it. So for instance, you can describe, if you kind of pick a fixed polarization and a fixed momentum, you can ask about what happens if I put a lot of photons with that fixed, if I think about a collection of a lot of photons with that momentum energy, if you like, and that polarization, if I start putting more and more of them together into the same state, what's going to happen? Well, if you put them together and if you put arbitrary large amounts of them together and you put them together, with the coefficients given by the, by this as a coherent state, you can actually get a state, you can actually get a quantum state where which is kind of labeled by kind of the light is kind of labeled by a magnitude and a phase, and it's really, that's the kind of state that you would use when you have kind of coherent radiation in a laser or something, if you want to. So this is the so you actually can, so such physical states are what occurs if you want to kind of do quantum optics and describe the state of a laser as a quantum object. It's not something that has a well-defined number of photons in it, but it is given exactly by one of these things. Okay, so I think I better stop there for now. What I want to do, so next time I'll try to summarize a bunch of things, but the one kind of loose end which I haven't gotten to is the one that Gian kind of asked me about earlier, is about, how do you actually, how I've told you about the Bargmann-Fock representation. All of this is a story of, well, what's the relationship between this story and the Bargmann-Fock story? And another reason for kind of talking about these coherent states is they allow you can set up the calculation nicely for this Bargmann transform of how to get from how to get from these Q space functions to these holomorphic functions, that the coherent states kind of give you a nice way of understanding one way of understanding where the how to transform back and forth between these things. And so I'll talk a bit about that next time, and that'll be the last kind of main loose end I want to talk about. Okay. So any questions about any of this stuff? Yeah.
So our final is given A is going to be tested in a virtual classroom.
Yeah. Well, I think it'll probably be I haven't quite figured out exactly how to do this, but it'll be something similar to the midterm.
It's going to be in classroom in Q3 or?
No. Everything is still virtual. It's all virtual, and it's again, it's essentially going to be kind of a take-home exam, like the midterm. Yeah. So you'll have a certain time. You'll have it for a certain amount of time to work on, but you work on it. Yeah, just work on it yourself. Okay. Yeah, it won't be very different than the it'll be some variant of the midterm, but we really yeah. Anyway, but let me see next Yeah,